Two presentations and again panel discussion like that we have. Without more delay, I request my good friend Subhashis to conduct the rest of the session.
Thank you, Shutta. Okay, good afternoon, everybody. I think we have the same format, two presentations, one by Mr. Blaurok, another one is Supriya Das, and then panel discussion. So without any delay, I would like Mr. Blaurok to take over. He's the one who is essentially responsible for this €2 billion project. So let's hear from him.
Yeah, thank you very much. I'm pleased to be here and to present here the FAIR project. I think another challenging mega project, I think an adventure usually. A mega project is all the time an adventure, especially a scientific one. And we are very pleased to show the progress and the status and the structure of this project here. Basically, FAIR stands for Facility for Antiproton and Ion Research and is a worldwide unique facility for acceleration of particles, and it's a driver like all large mega science projects for innovation and for technology and science. It is marked in the European context as a first priority of the projects for developing scientific infrastructure, and we are happy that many contributors from various countries are participating. You see all the flags here. I think an important one here, of course, India is also an important partner of this project, where we jointly work with all the partners on the realization of this project. I think basically you can see on the map here marked in brown all the shareholders, the partners here. It is India, it is Germany, it is Russia, it is Slovenia, it is France, it is Romania, it is Poland, it is Sweden, and it is Finland. So these groups decided at a certain point jointly to realize this mega project. And now we have an associated partner, which is United Kingdom, and since April of this year, also the Czech Republic joined as an aspirant partner. And the user community is 3,000 scientists worldwide, and we have a largely and very active community there, working for FAIR and already working on FAIR experiments, which I want to explain further. I think the idea of FAIR is coming from the early 90s or mid-90s. There the idea was born to build this project. Then in the early 2000 years, it was assessed and evaluated, and of course there's substantial funding required to say, yes, it is a scientific perspective, which is very good. It helps the mankind in many areas worldwide, and therefore it's good to realize this project. And then the search started globally who is interested to join this project, and just one example here on many collaborations here in 2017, the Indian and the German ministry on highest level said, yes, we want to do that together, and there the process to come together and to form an international convention between the shareholders started. And this contract was then signed with all these 9 shareholders on 4th of October 2010, and there all the representatives from the countries met together, at that time in Germany, close by to Darmstadt, where FAIR is positioned and located, and signed this contract. And since then, besides development, which was before, we are working on the realization and real implementation of the project. I think, and here we are talking about India. India is taking a leading part in this project. And when you see the map here on the side, just without going to the details, is a visualization of the various areas. 27 institutions from India are working closely in the project and developing over years in various locations, jointly together with the other international teams, technologies, new steps in terms of science forward to ensure that this mega project is realized and delivered, will deliver the scientific value. And here we have an overview of who is represented where. I think the steering group for a project like this is a kind of council, and in this council, from the Indian side, Mr. Zibai Raha from Bose Institute is member of this council, and he is also part of the joint scientific council, so scientific gremium for this project. These gremiums are all the time meeting 2 times a year, in July and in October, November, in this range. And then the progress and the next steps on the project are intensively discussed. And we get great support from everybody. In addition, we have from VECC, Professor Bikash, and then we have here on the administrative side, as usually, also in these mega projects, the financial part, the funding part is very important. We have a finance committee, and there are also representatives. Here, Mr. Astana and Mr. Bandari are in these groups active to represent the Indian perspective. And then we have further advisory committees, liaison officers, just nicely presenting myself here, Mr. Subhashish Chattopadhyay, and I'm very pleased to present here further details now. I think what is FAIR about? FAIR is just after the Big Bang. We are not the Big Bang, we are after the Big Bang. Since at that time, I think there were 2 elements, only 2 available, and then over the time of many millions of years, we have now the periodic table of elements available, where numerous elements are available. And we are interested in the questions, the scientific part, where and how does all these elements, especially the heavy elements, are coming from, how they are formed. And that is a question which is still today not answered. So the focus of FAIR is mainly fundamental scientific questions. But I think it's also important to know there are many applications coming out of these fundamental questions which are very important to the mankind, and a few of them I will mention. I think one important part is here, to give it in a broader picture, not only Big Bang and development of elements, is neutron star mergers. We have, I think, material is at certain point of time produced, and that happened, for example, through neutron star mergers. And there are many elements are acting. So how is a nuclei being kept together? How is material being formed? So on, there are various research pillars which are backed up with international collaborations who are looking into these questions. So they are named here. It is, for example, CBM. I come later to that. PANDA, NuSTAR, and APA. These are the 4 experimental pillars of the FAIR project. And they are answering fundamental questions about ourselves. The building blocks of life is an important word. How do we function? Why are we there? How can we think? How can we work? How can we operate? And how can we create innovative technologies? So FAIR is offering a lot of experiments and unique opportunities to investigate that and answer these origins, for example, of heavy elements. Another more concrete example is, a presentation before I was seeing space missions. If we want to go to Mars, there's a human being finally who has to travel quite a while. And this human being is exposed to radiation in space. And if we have not the possibility to protect the person against that, the person will simply not survive this long journey, which will be definitely many years. So we are selected, GSI and FAIR, as a preferred ground lab of the European Space Agency. And already now we are performing experiments with the existing facility GSI to investigate how can we protect or develop technologies to help people surviving in this environment. Another example is, and also that is in all these areas today, necessary big data. We have so many data and so many needs to investigate, to assess, to analyze data. This we cannot do anymore with normal computing system. So we need science computing, high performance computing in a different level. And for that, we have on the GSI campus for FAIR already built a so-called Green IT Cube. This is a 30-meter height building, a cube, and this is full of computer cores. So in the moment, it's only filled these 2 levels for FAIR, with the data which we will finally produce, it will be filled from top to the ground floor with computer cores to have the capacity to do all the analysis and calculation. And it's green core due to the fact that it is water-cooled and has a high efficiency in terms of using electricity and then also using the heat coming from this process. Another element is in GSI, and that relates also to FAIR. And last years is a cancer therapy developed, so it is possible to treat patients who cannot be saved by normalization. If you have in your head, in the brain, a tumor, a cancer tumor, the risk to destroy the person is too high, and nobody would operate a person like that. So therefore, I think over many years, methodology was developed to specifically treat these kind of tumors, and 400 people were treated on site of GSI to prove that this technology is working, and then it was put into the approval process to be used as a medical application. And there are several stations where people actually are today, as a standard procedure, are being treated with extreme high success rate. More than 90 or 95% of these 400 patients survived. And that is, I think, a great step forward. So that is basically the principle. The accelerator is hitting with a beam precisely the tumor in the head. And for that, of course, the head needs to be fixed and very clearly positioned. And by scanning the whole tumor, the DNA of this cancer is destroyed, and then it's disappearing. And the good thing is there's nothing what the person will notice. There are other therapies. You're losing the hair. You have a lot of, let's say, other impacts on the body from this. The person doesn't notice anything. And we want to develop that further. You see here another situation. If you have a tumor in the lung, then of course it is a moving object. It is not stable. So we are developing currently a technology. How can we follow with the beam a moving object and finally help people surviving if they are hit by this kind of disease? Another example is, I think nowadays people who have, let's say, a problem with the heart, so some rhythm problems with the heart, need to have an operation. I think what we are looking at is that you can do that also with a beam, so like a kind of scalpel where you don't need an operation, to ensure that the person can live and does not need for healing an operation, which would be also a great step forward. So, and this is now, after some examples, what is out of the fundamental physics, then finally also transferred into practical applied possibilities which are helpful for us as human beings. The facility. I think this year what you see in gray is the existing GSI. GSI is actually this year 50 years old, so a long-standing international laboratory linked with all parties, with India, with Russia, with US, all areas. And this facility is now 50 years old, and we want to extend that. And the key for FAIR is that the intensity gain is in the range of 1,000. So basically, it is much more science possible, it is much more analysis possible if we get the and of course also a kind of experiment can be performed by scientists in this facility. We also investigate antimatter, and we have of course very high precision in this facility, what we achieve to hit a target, to collect the data, and of course with a high performance computing to analyze the data and conclude on the results. So this is how it's looking like today. I think that's a picture from just 1 month ago. Here's GSI. And from GSI, if you have seen here, all these red lines are going into this new area. We are currently building more. This is a so-called, I'll go back one. This is a ring accelerator. This is 100, 1,100 meter circumferential. And that the depth of roughly ground slab is minus 17, minus 18 meters in the ground. Then this ring goes into a superfragment separator, where you here see all these black boxes. These are the experiments where the scientific people have the experiment installation and finally take measurements, take the data, and later on, here we have a collector ring in the southern area, and here a so-called anti-proton ring. That is the antimatter what I'm talking about. So, and this is what we are now in execution. I think we are excavating, we are building here the first concrete tunnel underground. And in December of this year, we will contract the civil works of the southern part, so that in spring next year we'll start with a civil implementation of this area. I think it's a lot of work. We are moving 2 million cubic meters of earth. We are pouring 600,000 cubic meters of concrete. So we have in some areas, and I look at the ITER project, that's also big dimension. We have concrete walls of 6 to 8 meters in some areas, which we need for radiation protection and for the general operation of the facility. And we will implement more than 65,000 tons of reinforcement steel. And we are progressing well. We started in July 2017, so roughly 2 years ago, with a groundbreaking ceremony. Here you can see that in this area. And after 2 years, we have built now the first tunnel segment in this position, where we finally did 2 years ago the groundbreaking. So great success. And teamwork is everything in large-scale project. And you see here the core team standing on top of the first tunnel segment and very proud that it works and could be delivered. And here you see also we have an outer tunnel. There finally the beam line with all the magnets is be installed. And we have an inner tunnel. The inner tunnel is with all the utilities, power supplies, power converters, whatever we need to operate the beam line is positioned there. And in between is there a radiation shielding to ensure that people are protected in various operation states. Here you see another important area in the middle of the facility. And I go back. We have here, in this area, the central systems of the facility, electrical, the central controls, and so on. And that's a large building, which basically is 180 meters long, 20 meters deep in the ground, and goes up to plus 20 meters. So it's packed with complex technologies, which are partially also in new development stages. And here you see the council, the International Council, I think, meeting, as I said, in July and December. The whole team visited in July now the site to convince themselves from the progress what we are doing. And if you are walking there and there's a ground slab where you're working on the right side and it is more than your personal height, then you understand that the dimension is big. So a very good feedback from the team there. I'm moving now to another area. This is the accelerator area. I think finally all the concrete, all the civil works is the house, which we are building for the core, which is the machine, the accelerator machine, to allow the scientists to perform the experiments. And here we have globally many contributors from all partners. Here an example that is module magnets who are superconducting. So we have the same technology, superconducting magnets, minus 269 degrees operating temperature, to allow that we can have this magnetic field and the parameters which we need for the operation and intensity of FAIR. And here you have a nice picture of magnetic power, for power converters for some magnets which are built by Electrical Corporation of India in Hyderabad. Tomorrow we will be actually there, so great job. And here we have quadruple chambers, other, let's say, components, which I will not go into the details, which are built in various stages in India, in Russia, in France, in each partner country. And of course, some are tendered in the industrial market, This is the way how we procure all these components. Important is also with the test facilities, all magnets who are coming to the site have to be, if they are superconducting, tested at that temperature. Build test facilities on GSI side, in CERN, in Italy, in various locations to test all these magnets prior to usage. And here you see again our power converters and other components. We have then also for the experiment side various components where also the Indian community is very active, and I will show some details of that. Here I'm coming to the power converters from company ECIL in Hyderabad. I think the team developed that, and that is also a kind of power converter which is not standard. It was a several years development phase to get the specification, the design and everything functioning. And after we finally released all the prototypes, we moved into series production, and that is now roughly in the range of 600 and finally 600 to 800 pieces which are produced here. And we are very proud to see here, I think, and that is actually tomorrow where we will release all these 67 pieces for shipment and then produce the other ones in the next 1, 2, 3 years. So then we have beam stoppers, other dipoles, which are magnet from the Indian collaboration team, which is also a very successful process. Coming back to the scientific part, I think these are the 4 experiment pillars which I mentioned. I think APA is focused on atomic physics and fundamental symmetries, plasma physics, material research, biologically, and the cancer therapy, which I was just talking about. CBN is dense and hot nuclear matter. NUSTA is nuclear structure and reaction studies, and physics of explosive nucleosynthesis, the R process. So, and we have PANDA, where we are working actually with antiprotons. And these groups are formed globally. I think APA has roughly 800 members worldwide. In CBN, we have 400 members worldwide distributed in various institutes. And here for CBN, I think the Indian community delivered quite a number of detectors, electronics, and that shows how this interaction and works give the products the quality of experiment equipment which is necessary for FAIR. NUSTA, about 800 members globally, and here also a number of experiments coming from the colleagues in India for the detectors and also for time of flight follow-up and other IT aspects. PANDA is about 500 members and works mainly with antiprotons. So we also said, I think it takes a while to realize a mega science project, and it is important that science can continue while realizing this new project. Therefore, with the existing GSI, we established a program we called FAIR Phase 0, and by that we are performing selected experiments in preparation of the large FAIR science, and that helps to confirm that components are fine and have the quality and have no surprises. On the other hand, it helps also the scientific community to work continuously towards the FAIR science program. And here you see a selection within the GSI facility where we are operating here at the various ends these kind of experiments, bringing results. We had last year the first beam time, this summer, this first quarter, second beam time, so that runs fine. We have a lot of interest from the scientific communities. Also important is to see we are producing jointly here for the global community a lot of talents with a very high qualification, which finally helps also to drive this innovation and the physics forward. And there are currently roughly 300 doctoral students in this talent factory ongoing, step by step, coming then to their final degree and moving on their career path forward. We have a Get Involved program so that we encourage students from all over the world to come to us to join for a period of time and get involved in the project. That's the intention. And we are happy that also from India several people are coming and are working in the team. So, another pictures from that. And I'm coming to the last two slides. I think one is just a word on how the procurement process works of all these components. Each partner country says, I have the capability in my country to do this part, and by that, in-kind contributions are allocated to this country. And then the country is, of course, delivering together, working with a project team, with a central project team. And this works very well. It offers a lot of opportunities to share knowledge, to develop innovative technologies, and to integrate that further in the installation and in the commissioning and operation process of the facility. Since we want that people from the shareholders are part in the installation, part in the pre-commissioning, commissioning, and in the operation. That helps to grow and to develop the community further. And of course, data processing nowadays works worldwide. There you don't need to be locally. And here's an outreach of the various activities. I think 42 groups are from India working on that, and that is a great pleasure on the contribution. Last slide for me, I think just summarizing, FAIR is an extraordinary opportunity for world science. It creates a lot of opportunities also for world-class innovative technologies, which we jointly can develop and share. And the common task today is, I think, we move forward in the civil construction, in the accelerator, procurement and designing, delivery of the components, aiming at first experiments in 2025. And we bridge the science period with the FAIR Phase Zero program to be active. And India, as a key founder and very active partner in this project, is a very important part of this, and therefore we are looking, of course, forward to a continued driving role and collaboration in this matter from all the colleagues here, especially from India. Thank you very much. Thank you very much.
Next presentation is by Dr. Visvesvaraya from
So good afternoon. I will mostly talk about the research program at FAIR and where India is contributing to the research program. And I come from Bose Institute, Kolkata. I will give you an overview of the physics program. So now, before just going to the physics, I mean, Mr. Blaurock has told you, but I just, for the completeness, I will just say that India builds FAIR. India does not only work at FAIR. So this is one example of the beam stopper, which is needed to dissipate 2-3 kilowatts of energy in only few nanoseconds. So this is a challenging job, and Indians have designed this, and they are going to build it. The next thing is the really important thing you have heard from him, that 600 of this power converter will sit, which will run FAIR, the accelerator. And 67 of them will be flagged off tomorrow from ECIL Hyderabad. This is a very nice success story about the Indian industry to the accelerators of the world. These are other things like vacuum chamber, and I would like to emphasize that the vacuum here will be again 10 to the power minus 9 millibar, which is same as the as in the LIGO tunnel, but the challenge here is a little bit different. LIGO has 4 kilometers long tunnel and a very high volume of the vacuum. Here the vacuum volume is not that high, but the challenge here is that you have to build this this vacuum chamber with 6 or 7 flanges, which has the mechanical tolerance in the millimeters, and you have to work with a very, very thin wall. So that's the challenge here. And we'll also design the superconducting magnets that will sit in the tunnel of the accelerator. So those are the accelerator components that will be built by India. Let's now move to the research program. So you have seen this scheme. So this is the existing GSI, the Heavy Ion Society of the Research Society, and this is the facility which is going to come up as FAIR. And FAIR is a multi-purpose facility, as we have all heard about. So there are 4 main research programs, but under each of them, there are multi-purpose research goals. So one is this compressed baryonic matter, which will work as the high energy nuclear physics research group, where we will test the high density baryonic matter. The other one is the new star, which will do research in the nuclear structure, astrophysics, and reactions. And the portion here is the SuperFRS, superconducting fragment separator. The other one is this antiproton and annihilation in Darmstadt, which will sit here in this ring. And the other one is the atomic and plasma physics applications, which will sit here. So a very, very wide range of topics to be addressed in covering in this all 4 programs. The beam of antiprotons, the hadron physics. So this is a hadron, and you see the quarks inside. Now the quark confinement potential, what is the potential inside the hadron that confines the quarks? The search for gluonic metals, the matter which is only, so we know that the hadrons are built of quarks, but there can be balls of glue balls. Search of gluonic matters and hybrids, so nuclear structure, double hypernuclei, all these things are this PANDA program. And then comes the rare isotope beams, nuclear structure and astrophysics, the new star program, which will basically talk about the nuclear structure, far off the stability line in the nuclear stability map, nucleosynthesis in stars and supernovae, how the heavy elements are formed in star. We had only hydrogen and helium and a little bit of lithium at the time of the Big Bang, but how these heavy elements have come up. So that's the goal of this new star program. The other one is this nucleus collision, the compressed baryonic matter, where we will, so you see these baryons now compressed together so that their boundaries break, melt, and the quarks and gluons are liberated inside. So baryonic matter at highest densities, which exists in the core of the neutron stars. Phase transition, what kind of phase transition is there? And if there is a critical point, there is a nature of phase transition changes, and the in medium properties of hadrons. And then there is atomic and plasma physics and applied science. They are highly charged atoms, matter at high pressure, densities, temperatures, and this therapy, radiobiology, cancer therapy thing, and material science. So this is the goal of this APA program. So now let us concentrate more on this compressed baryonic matter, and we'll have a journey to the center of a neutron star. So this is a kind of cartoon which shows that you have hadrons here. If you compress them too much, then the boundaries of these hadrons break or melt, and then you liberate actually the constituents inside, which are quarks. You can have the similar situation, similar kind of thing, by heating it up. And then at the end, what you get is liberated quarks and gluons, deconfined state of quarks and gluons. However, and this kind of situation actually exists in the core of the neutron star, where the density is 4 to 5 times higher than the normal nuclear matter density, where the normal nuclear matter cannot exist. And this kind of scenario existed in the early universe just after the Big Bang, where you had only the energy, and just after that, the quarks and gluons were formed. However, I will not talk about this, and we had a talk by the present session chair in the Alice session, where he talked about this scenario. We will be concentrating here on this. And this was a cartoon, and a more formal approach is the quark-hadron phase diagram, where you have the net baryon density on the x-axis and the temperature on the y-axis. So you can go to two extremes. One is almost zero net baryon density, but very high temperature. That's the situation which existed at the Big Bang, the early universe, where we had only the energy, no matter, so no baryon density, and this is the scenario. But the other extreme is if you have a very high, moderately high or high baryon density, but low temperature. That's the place where which exists in the core of the neutron star. And this is what FAIR will be trying to see what is happening here, what is the nature of the phase transition. If you reach the boundary of this, the end of the phase transition line here, if you can find the critical point there, that's the goal of the FAIR experiment, which is CBM. I will go into a little bit more detail on this. So how do we do that? How do we peep into the core, right? This is the experiment, the CBM experiment. And what is the physics case and the observables of CBM? The equation of state at the neutron star core densities. So how the equation of state goes in the neutron star? The collective flow of hadrons driven by this pressure, immense pressure inside this, particle production at threshold energies. So this is how, if you cut out a neutron star, this will look like, and this is the central core where the density is very high. Then you might remember our chairperson of this session gave a nice comparison of this Higgs program at CERN. If you go to charm bottom top, those are the heavier quarks, then almost 100% of the mass is contributed from the Higgs. But we are not made up of charm bottom top. We are made up of U and D, and they are only 5 to 10%. 8% of mass is given by Higgs, but the rest of the mass comes from in-medium modification. From the QCD. So that is where the in-medium modification of hadrons that will give us the signal, the understanding of how this mass contributes to our current world. New phases of strongly interacting matter, the phase boundary, the phase transition, this kind of thing, and deconfinement phase transition if it happens at high baryon density. Okay, so all these programs, all these physics will be addressed there. If you have, we can have the strange matters also. So all these things are part of the CBM program. And who are the messengers? The heavy ions collide, and then there is a fireball. So who are the messengers? Who will tell us what has happened? So these are the messengers. So if you go with time like this is the collision, and then the collision elapsed, and the particles are coming out. And these are the messengers, they come to our detectors. The rho that goes into E plus and E minus, or mu plus and mu minus, and the experimentalists put their detector to detect these, to go back to rho, to see if the mass is modified, what is the signature, those are the things. This is, of course, a simulation. And this is now the reality. This is the experiment. This is, of course, a simulated picture. As I showed you in the last transparency that the rho goes into E plus E minus and mu plus mu minus, CBM is an experiment where we detect both of these. So there is one detector for each. Each detects the electron-positron pair, and the muon detection system measures the mu plus mu minus system. And both of them does not go together. So you can have a time share of each detector or the muon detector. So at this picture, the muon detector is can be seen in the park position, and this is where India is going to contribute. This is the detector will be built in India and put into the CBM experiment. So this is a little bit more detailed view of this detector, of course, in simulation once again. So what you see here is the target. The beam comes here, hits the target, and there are these silicon tracking stations inside, and then the muon detection system, which is, you see that these green things are the absorbers. So to detect muons, you have to absorb other charged particles. They are garbage to the muon detector. So we have the detector station sandwiched between two of the absorbers like this. So and then finally these are the two muons going together, going like this, and they will give signal to the muon chamber detector, and they'll be detected. And finally, the mother particle which created that those either it is rho, omega, or phi, or j psi, will be reconstructed from that. So Indian responsibility is first, second, third, and fourth station. You see the first, second, third, and fourth station, and all stations cannot have same technology because of the number of particle, the particle density on the stations. So they can have different technology. The software needs to be optimized for different kind of thing. So that's where we will contribute. Challenges in the muon detection is very high collision rate. So detector has to be very, very fast. The fast plane have a high density of tracks, so it has to be very, very thinly granular. You have to have very many cells of the detector in a closed packed zone. So it has to be radiation resistant because the high neutron dose, the detector will be there sitting for 5 to 10 years lifetime. So the radiation will have an effect on this. And it has to be a large area detector. You have seen the area of the detector. Data has to be read out in a self-triggered mode. So all these things have to come up with a solution. And the solution exists. The solution is this technology, gas electron multiplier. What you see here is a polyimide foil sandwiched with copper planes on both sides, 50 micron hole diameter, 140 microns of pitch, and then you apply field, and you see how it works. So this is what is a cross section of this. So these are the copper, thin copper, 5 micron copper plates, and this is the polyimide. You have the hole, and when you apply voltage here, this is the field directions. And what happens is this is 50 micron, and you put some few hundred volts, and the field inside becomes very, very high to produce the avalanche. So you have one charged particle here, you have many there because of this avalanche, because of the multiplication. And this is how you detect the particle. Now the electron multiplication takes place in the holes of two copper foils separated by kapton. That's what it is. Amplification may use 2 or 3 stages because one may not be enough to detect the charged particle. The maximum size is about 100 centimeter by 50 centimeter of our detector. So the basic elements of a gem detector is a drift plane, amplifying element is the gem, and the readout plane which reads out this. And then you will have cascaded gems which gives the higher gains and have lesser spark probability. The main characteristics of this kind of detector is rate capability. As I said, it has to be very high, the high rate. Good position resolution because you have many, many tracks going, so 2-track resolution depends on the position resolution of the detector. Very fast time resolution, and the readout flexibility to have the triggerless data acquisition. So this is how this staged, cascaded gems can work. So this is the drift plane, this is the readout plane. You have 2 stages, you can have 3 to increase the gain. So this has 3. But one more important point is, as this detector has a very, very high good position resolution, this as an application, they have a potential application in medical imaging. If you have a chance to go to the fair stall, you will have a picture there. We used the gem detector to have the imaging of a fish bone. So you can see the fish bone imaged. So this has a very, very high potential for application in medical imaging. This is a spin-off from this detector technology. And this is how we started the fabrication of gem prototypes. We have a very small 10 by 10 gem prototype like this. Thermal stretching was used, and then from 10 by 10 we went to 31 by 31 centimeter large size gems, which was done at VECC. And then, as I said, we had 1 meter by 50 meter detector. So this is a 1 meter by 50 meter gem foil, and then the drift. So this is the foil you see, which is the gem, as I said, and this the drift and readout PCBs. This is another point which I want to emphasize, that these readout PCBs were made in Micropack Bangalore, where again this industry relation with the R&D projects of these mega science things come into picture. So then the framing of the large foils. So you have a large foil. I mean, handling a 10 by 10 gem foil and handling a 1 meter by 50 meter gem foil is not all the same. So you have to be very careful. These are very thin foils. You have to stretch them properly. Otherwise, your electric field inside go mayhem and it doesn't work. So you have to be very careful with the spacers. You have to be very careful with the framing. You have to be very careful with the stretching. Everything has to be very careful to make a large size detector and handle it carefully. So then finally it is framed. It is put together with the frame and the readout PCB. You can see the cuts here where the connectors come out from the detector and you put your readout electronics there. Okay, so this is the assembly of the prototype. And then finally, you have to test your detector, and this is again done in Jülich in Germany. There you put the detector in the beam line, and what you see there are this. This is a standard, the ADC distribution, but more important things are here. So this is a cell multiplicity. That means if you increase the voltage across the gem foil, for one particle, you hit one place. So if you hit one particle, you should get one particle, right? So it does not blow up on your detector. That's what you see here. You see here that with the gem high voltage, I mean the gem voltage, your efficiency goes to 95% or little more and then stays there. Okay? And then, as I said, that this has to be highly rate capable. So what we did is we changed the rate of the beam, and then what we saw is the efficiency never goes down. So that's one important point, that the gem has to be rate capable. Same thing for the gain. So you increase the voltage, definitely the gain goes up. But most important is you increase the rate, the gain does not go down. Okay? So that's what it says, that this detector is capable of using in the experiment. Okay? However, we still continue the R&D with small prototypes for different reasons. As I said, this detector will stay there for 10 years. So we don't want to see a degradation of the detector with the accumulation of charge. That's what we are seeing here. So this is what is the normalized energy resolution of the detector. And this is, so what we do here is we have a small prototype and we put a iron 55 extra source on top of it and keep on radiating it and see the energy resolution from time to time. And we see that as we are accumulating the charge per unit area, and this is a high number, this is a large number, the energy resolution does not go down. So there is no degradation of the detector for this large charge accumulation. And we are also trying to try different technologies for different things. This is a RPC. Another thing is that you have to make the cooling. So the detectors, when the electronics are fit to the detector, they are hot. So we are trying to make a water-based cooling system for the same detector. And what you see here, that has been put to the beam for testing, and the proof of principle has been already done. So we will make the cooling system also here. And we are also getting ready for the production. So we have to have about 150 of these gem modules in India. So we are building a clean room, actually two clean room facilities we are building in India to produce this detector. Finally, we have to deliver this detector. So as the accelerator parts are deliverable, for us the experimentalists, the detectors are also deliverable. So we have to deliver the detector, then only the experiment can take place. I just thought that to put few names of the, I didn't have an idea that in last 5 years, so many PhDs have been done. So we have not started the experiment. I thought there will be only few, so I just started putting the names and things, and then we completed almost 2 per year PhD in CBM only before the experiment has started. So we are still 6 years, we have, and if you just read out the names, so there are very many different data communication, the detector, the simulation, the physics, a lot of different topics. So PhDs are, this is for the students, so you come here and get your PhD done in this kind of thing. And I am also happy to say, I could not put the summer students' names here, who are doing summer projects, that this is being recognized somewhere else. So this is on the CBM thing, overview of the detector of muon chambered CBM experiment in the Jefferson lab, this school in 2019, and our student got the best prize award there for this work. So this is also recognized. So now we will briefly touch upon the other experiments in New Star. What are we made of? So we are all made of star stuff. We all know that. But what are the stars made up of? So stars are made up of hydrogen and helium, okay? But then, in the later stage, you have carbon, nitrogen, oxygen, etc., and heavier elements. So then, if you can try to see what is the composition of human body, you can see this list, and then you see 95%, 95.7% are these, and this is in the stars. So we are made of star stuff. But how does it happen? So stars have the same elements which constitute the human body, right? How does it happen? So this new star program is going to see this. Highly energetic heavy ion beams are shot to the target. The fragments, the exotic nuclei, resulting from these collisions are sorted using a superconducting fragment separator. This is a sorting machine. Yeah, I'll just. The nuclei are then studied for their lifetime shape and internal structure using different detector system. Okay, so this is the superconducting FRS, and the new star facilities will be coming up here. So India in New Star. So like India is in CBM, India is also in New Star, and this is the detector activity going on in different places in India. This is the D-gas detector, and this is the monster detector, and there's another activity of studying this very fine structure and lifetime in the trap system. Okay, so this is what India is contributing in INSTAR. And up ion plasma physics applications are there. There are a lot of atomic physics activity going on, plasma physics and biophysics. The most important is the cancer therapy. And APA experimental facility will come up like this. This is the APA cave. This is the cold relativistic heavy ion and ring here. And this is again ESR. This entire thing is for APA facility. And then there is another physics program, research program, is the antiproton annihilation in Darmstadt. So which will talk about the hadron spectroscopy, as I said, exotic QCD states, the structure of hadron, spin of this thing, and of course the hypernuclei, etc. And this is the Panda spectrometer, the way it looks like. The detector requirements is 4 pi acceptance, high rate capability, momentum resolution, very nice momentum resolution, good PID, Cherenkov detector, top detector, and all other things. And this is again the same slide showed by Blaurock. These are the Indian institutes and universities in the collaboration. So we are all over the India, spread over. And this is joining hands to make it a success story. So in a nutshell, this is what is India. India is building fair. Key accelerator components are being designed and fabricated in India. Indian groups are participating in fair physics programs, developing detectors for both CVM and New Star experiments, and participating in APA and Panda program too. Well, at this moment, not in a very big way, but we are trying to catch it up. A large number of collaborating institute universities all over the India developing the human resource for the future, in for this experiment, for other experiments. And then a very important point is various Indian industries are involved both in R&D and production of accelerator components as well as the experimental deliverables. So that's it. Thank you for your patience.
Sanjay Ghosh of Bose Institute, Calcutta, Professor Jürgen Gerl of GSI Darmstadt, Germany, and Mr. Y. Rangarao from Vacuum Technique, Bangalore, to come onto the stage and conduct the panel discussion.
Hello, everybody. Good evening, everyone. So this is the last session, and I'm not sure whoever thought this last session was there, whether they are here or not, actually. But anyway, most of you have heard that FAIR has actually two parts. I think most of these mega sciences have that. One is the accelerator building, so the components and those kind of things, that has a big industry collaboration part. And one of the idea of all these mega sciences were to actually have a good collaboration with industry, which in India is still in a very nascent stage. And of course, then is the science. For the science, as Supriya told you, building up detectors to actually put it in the experiments and do the experiments. So these are the two aspects of that. And what we'll do in this panel discussion is, as I said, one of the part was the industries, but I don't think there are much there. But what we'll do is that following way is that I'll ask, with me I have Dr. Jürgen Engel. He's a nuclear physicist, well-known nuclear physicist, and he's also part of the technology director of the technical director of NewStar. So one thing you have to understand is that just the things, in-kind things like beam stopper or vacuum chamber or power converter, they are not the only thing that the CBM has or this FAIR has. There are a lot of other things where actually Indian industries can participate. So I'll request Jürgen to say in few things in short some of the bigger aspects of the FAIR in terms of science as well as the components, hardware. And also I have with me Mr. Rangarao, who is the Managing Director of Vacuum Technology Private Limited, India, Bengaluru, and he's actually one of our collaborator in for vacuum chamber building. So he will also tell you a few things in a short about his own experience. And if you are still awake, I hope there will be some question for students or you to have little more lively thing. Thank you. So you get.
Okay, it's a pleasure for me to be here. You heard already from Jörg Blaurock how big the FAIR facility is. After all, we are talking roughly of something like 2 billion euro. Half of that obviously goes into concrete, also in building all the houses we need. But the other half, roughly 1 billion, really goes in all kinds of machines, in equipment, in experiments. And this is for industry certainly quite interesting. And as Jörg said, we have this in-kind system where the companies, or where the countries involved in FAIR essentially look for things which could be interesting for their industry. And so they have these kind as in-kind contributions for the benefit also of the industry. Otherwise, we would not spend so much money on basic science. And but I think this is not all, because we are in a worldwide competition nowadays, and this global competition gives you also a chance to go beyond what is in this in-kind packet. And if I think of what kind of items, what kind of components are needed for FAIR, so it really covers everything. So we have from very simple cast iron, where you have not to have a high-tech industry for that, but simple things can be built here. But we have also superconducting magnets, as we heard. We have vacuum chambers, we have RF cavities, there are ASICs, electronics. This is already fields where India is involved, but could get a bigger share of the whole thing. There is software, there is FPGA programming, so it's also services which are needed. All the IT engineers, in particular here in Bangalore, they could also take a much larger part of the FAIR project if they would be aware of it. So all this engineering is certainly a field where India is not yet well represented. And now if you think of what is the reason for that, I think we as FAIR, we are not sufficiently known by Indian industry, and vice versa. FAIR does not know what Indian industry is capable of. So I think there is still some parts where one can improve things. And I don't know, maybe from the point of view of industry, it's not like that. Maybe you are aware of that, but this is at least how it appears to us from the outside.
I think my suggestion is what you said is perfectly right. There is a software, lot of industries. Sorry. Now, Bangalore is known for software industries. What you said is perfectly right. But only thing is, this whatever you are conducting yesterday and today, it's not spread to all the industries, all the institutes. It would have been better even if to the software industries this is spread.
That's right.
And that would have been helpful to organize this in a better way.
So other thing is that from both of your side, the interaction part, whatever we are involved in already, and whatever your idea, your experience is in your interaction with the scientist, or the these all funded by government. So those part, whether how much that thing is smooth enough, or other than the information part, that's all we know. There is a lack in the information, or we have to do a little more about that. But other than that, the interactions or the communication part, how is it?
No, as I don't know whether all of you know about it. I am involved in the manufacturing of these vacuum chambers for the SPADE project, and we have been given the contract. And we have made two mock-up units, 3 chambers we made mock-up chambers. And today I have shown it to Dr. Blarak and other people. It looks to be that we have achieved almost 95 to 96% what they expect. And the accuracies are very critical. And there's a good communication, absolutely there's no problem. And as now we have more confidence and we are more confident in contributing for other projects also. We have also participated for beam stopper. We have given the bid, and we hope that we will also be given chance. And I'm very happy that to involve in such a challenging project on this. We would like to involve more and more in this challenging project.
Yeah, thank you. You want to add something?
Yeah, so maybe one should also mention that we have, from the industries which are involved currently, we really have many good experiences. So these people know what we are doing, they are capable, they can really make a positive impact on the whole process. And as was also discussed in the previous panel, of course there is really high-tech involved in that. We are going to the frontiers of what is technologically possible nowadays, which means also for industry, it's not just a product like any other product, but we have to go through a learning curve before we can go to production, which involves a lot of prototyping. One has to be open for new ideas, for new avenues to proceed with. But in the long way, I think it pays out. So this is the way forward. And in particular for countries like India, I think this is the future. Maybe I should also mention we have in FAIR very strict quality assurance conditions. And some of the companies we are working here in India, they don't like this too much because this is an extra burden. You have to make a lot of documentation, for instance. You have to really prove that you can produce high quality. But I think in the long run, this is also beneficial for these companies because then they can really become global players also. They can be in the upper league of companies in the world. And for this, there is no way out, so you have to do it. And FAIR is a nice playground, so to say, to learn all these things and get experience in that. So in that respect, FAIR is also a good opportunity to really involve or evolve the Indian industry.
Thank you. Is there any addition from the audience on this particular topic of discussion?
As you just heard from our speakers, India is actually a founder member country of FAIR. So, in fact, all tenders that are put out by FAIR are open to Indian companies. So, in fact, it's an appeal and it's a question to our industry friend here that I think it's high time. Okay, one is that we are, we need to supply something. We are approaching you. We go through this cycle of, prototyping, quality control, and then we finish our commitment. But I think there is an opportunity there in these projects now to bid for those open tenders. And on our part, I think Subhashish ji is also putting all those tenders on his website. We have also linked it to the DST website, and I think they all appear on the FAIR website. See, such opportunities were not available in projects earlier. See, for example, in CERN, it is available now that we have become an associate member. So those tenders are all, we can compete for those tenders. FAIR has always is open to us. Is open to all of us because we are a founder member country there. So I think it's an appeal to our industry friends that we should actually aim a little higher and try to bid for those open tenders also. Because speaking from the government, if we are able to only supply the items we are supposed to supply, it's seen as an investment, it's seen as an expenditure. But if you are able to win some tenders back in an open competition, then it will be a big plus for all of us, and it will help people like us to advocate and to argue for such projects more forcefully in the government system. Definitely.
Yeah, we've been doing that, sir, and now I think recently one tender we have downloaded from ITER also, and earlier, and earlier we have participated and we have also won the contract for ITER directly in the international competition. We have supplied also, and we will do for FAIR also. Now we participate. Yeah, sure, sure.
I was just going to tell you the same thing. Thank you for your comment that the FAIR tenders are open to this, but this auditorium now, I don't know. We have to find a mechanism to spread this word. So how do we? He's from industry, but I don't know how many of the industry people are there in the auditorium at this moment. So how do we spread this word? Can we call some industrial body, something like that, that we spread the message to them and then it goes to the industry? So
yes,
we have to find a mechanism to spread the word also.
Yeah, I have a suggestion that there are industry bodies like Karnataka, Acacia. There is one industry body like Pina Industries Association, where the lot of engineering and precision engineering industries are there. And if this, suppose today's panel discussion, if it was done, it was announced well, it would have been possible. Even people like us could have helped you. But to be honest with you, I didn't understand.
That's why I understand. I agree with you.
I think we can do one more meeting or something like that. And definitely we can organize in a better way.
Yeah, definitely. We have a program again in Calcutta. It's the continuation of that. We hope we will be able to do much better in that scenario. You want to say something, Subhashish?
No, I just want to add something that Shumon is here, right? So Shumon is the industry liaison officer with CERN. And he has been, because CERN, associate member, and then a good amount of money is paid every year, and then questions are being asked all the time that why is this. So one benefit is being said is that our industry can participate directly, which is true. But then at the same time, the products which should go there should be useful for CERN as well as for FAIR. Now, Sumon has been trying his best to get all the information from CERN, trying to spread it out. I have been trying in FAIR front, like Dr. Asthana said, to give all the information, talking to people. In fact, we organized 2 industry meets for FAIR in Hyderabad itself. The first one had like 26 industry participants, and the second one is a little bit reduced, but we, as Mr. Rangarao said, that there was an enthusiasm from the industry. There is no doubt about it. But then it has to be continued. It should not be just one-off procedure. Now, in my opinion, all the mega science projects, they are involved in a range of products, whether it's vacuum chamber, whether it's RF, whether it's software, which is true for everybody. So it would be very useful to have it some, I don't know whether it's website, but it's a regular meeting, and where the industry will be called specially for that, and then try it out. And we have to have colleagues from like Mr. Blaurock and others also. It cannot be just one way around that we just say, no, you come and then take the order. So you have to also find a way. And as Dr. Asthana said, it will be really a positive thing for all of us in our effort. Do you want to make any comment on that?
I think definitely a point is to improve the communication information flow, that I think early enough it is for everybody clear what kind of technology packages are available in the project, and then each partner or group or industry can find out what is of interest for them. And this kind of communication preparation, I think, definitely is helpful to be also successful then in awarding. Just sending out a tender sometimes is not helpful, since the scope and content cannot be fully understood.
That's right.
Exactly.
That's right.
So this process needs to be, let's say, more practical, organized, that people and industry can prepare for that and say, even if you want, for example, what was touched on, to form a consortium, a group of companies, I think this takes months, sometimes a year, to bring companies together to be prepared to bid for a larger package. And this information flow is something definitely which is to be reinforced, I would say.
Definitely. Thank you.
Sir, I have one point. Actually, this for the CERN, for example, Mr. Suman Sarkar actually he knows about, we have been doing certain components, accelerator components and other things for BRC, VEC and other places. And knowing that, for the last 3-4 months, he has been bringing it to our notice regularly, these requirements for the CERN project. And he has been meticulously following with us to give a quotes and to submit and informing us the status of the quotes, etc. And maybe a similar person for the fair may help to identify. Like us, many people are there. It is not our industry alone. There are many industries who are much competent enough and all that. So something like that may help for the fair project also.
One second. Let Jürgen.
It is directly related, because I
you want to add that
too?
Okay, go ahead.
Continuing with the discussion, means there was a requirement for a vacuum vessels, which was around 12 meters long, and it had to be machined in a single setting. For that, basically, industries has to invest a bit, maybe in the beginning, and maybe reap the harvest, as Professor told, that we have to have some patience and we have to invest maybe in the beginning, because we cannot make the profit right in the beginning. And in long run, definitely there will be very good opportunities.
It's true. This exactly brings me to another twist in the whole thing. We approached in some sub-project also local industry here, found very clever engineers who would have loved to take part, but they said unfortunately they cannot compete because some infrastructure is missing. And maybe this is a task to DSD and DAE to check if one could not help these companies to develop this kind of infrastructure, to make them capable, to empower them in a way that they can take part. Because after all, if an industry first has to invest billions, or not billions, but many millions to become, to be able to compete, then this is also not good for them. So this kind of industry policy might also be tackled.
Yeah, that's right. Thank you.
I think we recognize all the problems. It's just that we don't have, we haven't really thought of the solutions. One is increasing communication, which everyone has talked about. I think we have made some headway there, but it still needs to improve. The second one is that I think people have also told me, and this is what I hear, I keep hearing from people, that many of these, the tendering process, the tenders, to understand the tenders because many of these companies are not very big companies, so that they don't have that they don't have that kind of overheads to have that kind of system. So understanding tenders is another problem. Then to write tenders, they need some help and things of that kind. Third is that upfront R&D expenditure. Okay. Now, so these are various challenges that we have, and our institutions also have the challenge that, okay, I mean, how do you, within our financial rules, how do you give a tender which can allow for all these things? So that's another challenge. But one other problem, and which again brings me to the point that I mentioned in the beginning, that, for example, in the CERN, in the earlier part, there are many companies who invested a lot of money in the R&D, you see, in setting up the infrastructure. And then suddenly those things were supplied, and then they were out of job. Then a couple of them, in fact, came to me that what do we do with this in a fancy semiconductor thing that we have set up? We have no job. So that's why I'm saying, I think if we have this, these industries, because we also hope that there will be more such projects in future, one after the other, we hope. But all these projects require a lot of investment. We don't know how it will take place in future. But such laboratories will exist in the world. Such machines will be built in the world. I think we are becoming more and more open a world. I mean, you know, so there will be opportunities if we get into the habit of competing for open tenders wherever available. So that will help you to keep doing this things on a continuous basis. If you have already spent something to build that R&D capacity, the initial investment, and okay, if not in FAIR project, some other project, it need not be funded by us, but some other project. So you know, whatever you have done, it will be of use.
It is very important to this open.
Thank you.
Yeah.
You
just
go
one.
ahead. Yeah. Go ahead.
Yeah. So, sir, just one small comment is that, so in this tendering procedure, when we work, sometimes a challenging job comes and we have to prepare a price estimate before even putting the tender.
Yeah.
So in that way, we even don't know that what are the capable companies are there, because if we Google, we don't get all the list of the companies.
Okay,
so at least there should be some mechanism that there is a list of the companies with the most challenging job of that field which they have handled.
That's definitely a requirement.
Yes. So at least we should be able to know that whom to contact, at least the genuine person of that field, to get at least a genuine price estimate for that.
I think this is some serious issue. I mean, I think we had some discussion on that.
Yeah, that is our job. That is our job to put together.
Definitely, we need to do that.
On the engineering side, there is no depth of infrastructure. There is enough infrastructure available, but it might have spread over many industries. Somebody can utilize. One industry may not have all the infrastructure required. But enough machinery, engineering side, there is no depth on that. And similarly on the software side, I think we are as good as anybody else in the world.
Yeah, so that's exactly is the kind of thing we need to do. We have to put all the list of all these people who are capable of doing something or other. Okay. You have anything to add?
Yeah, maybe another point. We are now talking about a horizon of 6 years until FAIR is built, but then the game is not over. So you should think once we are running with FAIR, then we still continue to make our systems, our experimental setups better and better, also our machines. So there's a constant development going on. And we saw this in the last 50 years at GSI, where we really made a lot of progress also in technology. And this technology is also interesting for industry. To give you some examples, already now in the engineering part of FAIR, so we have new products, so to say, invented in a way. So there is new fast 3D graphics, which you can use for gaming, if you like. There is cancer diagnosis, which is always becoming better and better. We have found a way for energy harvesting, which is right now also a big topic. Environmental monitoring, all these fields requiring high-tech, they are all fed by inventions, developments, and ideas which are coming from our community, from FAIR in a way. And so you should not just say, well, in 6 years it's over. You should see this really as a continuous process where you can always, with the scientists from India involved in, you can always get your hands to these things and exploit them. And currently this is also not really well established. I'm aware only, for the New Star part where I'm responsible for, we have only one IIT which collaborates on this kind of technology transfer businesses. And I think there is so much to do there. This is also a good chance for industry here.
Yeah, definitely. Thank you. So anyone wants to add there anything? Okay, so we can wrap it up by, I just want to point out one more thing, that this is what something we are speaking with among ourselves, that if we take the whole spectrum of these mega science projects, there are a lot of R&D, there are a lot of scope for innovation. And maybe we should plan to have these IIT guys, engineers, and even the university students together and put those innovative sides to them, because we don't really have them with us. We always miss them. We have only few research scholars which we get them putting the ad on the newspaper or websites, but we need to take this message to them also, because there are a lot of, I have a feeling that there are a lot of innovative scope for innovations there. So we need to plan that also. So just like that, for the industry we are planning something, we need to plan for this innovation side, for the students, for the people who can actually contribute hands-on. So with that, we'll end this panel discussion, and I hope in Calcutta we will be able to take remedial measures for some of them. Okay. Thank you.
Thank you.
Thank you, Sanjay, for conducting this session, this nice session. So I think this is now our pleasant duty to hand over some memento to the panelists.
So, without any further delay, we come to the last, the last session, but also the most important session, because I'm very happy that the fair panel discussion went very, very well. It also opened up a lot of things which I actually noted down, and I'm sure we will take them forward. But so let us hear on this perspective more from the industries themselves. We have 3 sessions. So the industry chair here, 1 session, 3 speakers. Suman is going to conduct this particular session.
So we have come to the last session of the day, and I assure you that it will be to the point and very compact. We had in this Vigyan Samagam Bangalore, we had 10 industry stalls, and everybody participated very enthusiastically and put up their displays, and I thank all of them for that. And we had shortlisted 3 panelists based on their area of expertise, and as we cannot invite everybody, so we have only shortlisted 3, and we would like to understand their perspective about the Vigyan Samagam. The panelists are Mr. Surya Narayanan from L&T Valves, Mr. J.V. Nayak from MS ITMI, and Mr. Dinesh Kumar from CT Controls. Regarding Mr. Surya Narayanan, he is working in the field of customized valve design for extreme applications like nuclear, cryogenics, and space. And they have undertaken very important and efforts to outreach with CERN project. That I hope he will maybe touch upon that. Mr. J.B. Nayak, he has recently received a contract for manufacture of components for superproton synchrotron from CERN, and he is basically involved in precision machining, welding integration, and inspection, and he is also involved in drift tube LINAC tank assembly components for Fermilab, I think. And regarding Dinesh Kumarji, he is involved in designing manufacturing instrumentation systems, especially for sodium loops in India's first PFBR, and he is also participated in CERN market surveys for low voltage and extra low voltage power supplies. With this brief introduction, I will request them to take the seat. And maybe we will hear from Mr. Surya Narayan first.
Good evening, one and all. From L&T valves or big spectrum of L&T, we have always been involved in defense, nuclear, and aerospace projects right from the beginning of developments in India. And our interactions with CERN recently has been very wonderful, and we could successfully register as a supplier, potential supplier for the CERN projects. And they have been extending their support very nicely, and even in fact my colleagues Mr. Mahesh Joshi, who is the chief executive of L&T Valves, and Mr. Durai Raghavendran has visited the CERN facility recently. They thanks to the courtesy by CERN personnel and procurement group, and specifically they were very courteous, and they extended their support. They took our people around all the CERN facilities, especially the large Hadron Collider project in Switzerland. And a special thanks to people like procurement people like Mr. Nordine and Pierre Lott. And from L&T valves, we have been making valves for very severe applications, ranging from very high pressure and very high temperature of supercritical applications to nuclear, of manufacturing mainstream isolation valves, up to cryogenics. So we have been doing this, and for mega science projects, maybe we have to get involved, and we are always excited about it. And we have supplied a few valves to ITER projects, but they may not be so critical valves, but we have done some supplies. And more than the commercial aspects of it, these kind of mega science projects, what it does is it expects industry to stretch itself a little more. And the benefits are not in the short run, it may be in the long run. You will have a lot of learnings, and you may have a lot of collateral benefits which we may not realize in the near future. But it is certain to come when we get involved in such mega science projects. So and we can develop as a nation as a whole, and in developing cutting edge technologies and indigenize a lot of things which are not available in India so far. So and one of the feedback from industry is, please involve us right from the beginning, in the sense in the matter of freezing the specs, or because that's where a lot of things happen. When we put in the specs, we think it's okay, it can be done, but when we actually come to doing it, there are a lot of gaps. And by the time there is much time has flown, and there is less time to bridge the gaps between what is required and what is practically possible. Or so if industry players like us are involved right from the beginning, it will help us to bridge the gaps. We will also understand a lot about the mega science projects. Probably this Vigyan Samagam kind of thing. We really came to know what are the big science projects going on, and more than reading in the Google or Wikipedia, it makes a lot more impact in coming here and attending what people are doing all around the world, and how we can contribute to it. And it will be an exciting journey to contribute to such developments. So thanks to one and all, and I welcome all of you to visit our state-of-the-art manufacturing facilities at Coimbatore. And we have been making valves for in defense, nuclear, and in aerospace applications with extreme customization, a lot of customization. Thank you one and all.
Thank you. It was very well summarized, but one small point I would like to make is that in case of CERN and as well as in case of FAIR, I think these technical specifications are basically built to print. So in-kind contribution, where in-kind contributions are involved, there definitely we should get involved with the industries right from the beginning. But in tender mode, definitely we have to build to print. With that, I will just move to Mr. J.V. Naik to give his perspective, please.
Hello, good evening, ladies and gentlemen. It has been a wonderful experience for us for these 2 days. We have interacted with so many Indian scientists. We have explained them about our capabilities and our development projects. And we have done a lot of projects for electromechanical assembly for BRC, ISRO, LPSC, TIFR, L&T, Godrej, and the Space Application Center, Ahmedabad. This was only possible because our friends in this organization, and thanks to Mr. Suman Sarkar, with his reference, we got the CERN project, a small order we got from CERN for manufacturing of flanges. So we are thankful to him for introducing us to CERN. To explain about IDMI, IDMI has mainly 4 activities: design development, manufacturing, and training, and calibration. In design development, we take development work, and in training we train people, nearly 13,000 people we train in different fields, and in calibration we have mass, volume, temperature, flow, and dimension metrology laboratories are there. We have got very sophisticated equipment for calibrating purpose, right? And for mechanical workshop, we are manufacturing press tools, mounts, die casting dies, fixtures, and all, and also electromechanical assembly. To name a few of the projects we have undertaken are non-contact type limit switches, and a double crystal monochromator for RRCAT, absolute pressure sensor for BRC, ultrasonic flow sensor for BRC, pipeline inspection gauge, single alpha and 3 alpha for Astro satellite launched 2 years back for TIFR, ultrasonic water level sensor, 6D PKM robot for neurosurgery, quadruple electromagnet developed for BRC, and they have supplied it to Fermilab USA for their accelerator program. EDM machining of vanes, of rotors and nozzle block of GSLV Mark III. Recently, this Chandrayaan launched some GSLV Python. It is having IDME manufactured parts. And we have made a twist block and multiple waveguide for RF components for Space Application Center, Ahmedabad. We are having, we could develop this because we are having a skilled manpower for designing and manufacturing. Also, we have high-end machines like CNC milling, CNC lathe, CNC sparkergen, CNC wire cut machine. Also, we are having inspection dimension metrology lab, which is enable accredited lab, having 3D CMM machine. So we are now on behalf of IDMI and myself, I invite you all to this our IDMI, and you can look at our facilities in IDMI. Thank you very much.
Thank you very much. In short, if I just wrap up whatever he has said, they are very good at precision machining of jobs, and such kind of requirements are there from, I think, all the projects. And with that, I'll just conclude Mr. Dinesh Kumar to give his perspectives.
Good evening. Let me thank Mr. Suman Sarkar for asking me to come out to stage, because it's an opportunity for me to express what a small-scale SME sector feels like, and we talk about science projects. See, in yesterday's talk, Professor Ramamurthy as well as Dr. Kakodkar. I spent almost all my professional career in an SME sector. So whatever I talk will be mostly based on what SME perspective is. So yesterday when Professor Ramamurthy and Dr. Kakodkar was talking, they emphasized that mega projects requires mega money, mega funds. So when a small scale industry aspires to do some project for a mega science project, it really means that we also have to have mega funds. That means every science project involves a lot of innovation, lot of work in the R&D sector. So we put in that much effort. Where do we get the funds from? See, from my experience, I can tell you, we have been working with the DAE for a long time. And many a time what happens is we put in our money, our effort, and our R&D time to develop a project. And then we have to go around when it comes to a so-called tendering process. And we don't have any guarantee that whatever effort we have put in, whatever prototype we made in, will be will come as an order to us, because it again goes to the lowest tender process, whatever it is. And even if we manage to get an order, what happens if we, in addition to whatever money we put in, we also put in again a security deposit 10% to start executing the order. So why I'm telling you this, most of the work, see, small scale do have a very high potential, technical potential. People are there. But where do we don't have money. The banks doesn't give money. There's only talk what we hear from everybody. When you go to a bank with a requirement, normally we don't get any help from bank. So my request is whether DST and other group, DA group can do something about this. When a small scale industry puts in some effort, in their time and their money, somewhere they should be able to make sure that that money they get back. Forget about the profits on the number of units produced. In many of the science projects, what I find is many a time it ends up with only few pieces. There's no scope for the mass production. So it's only what we make in the initial phases, maybe 10, 15 numbers, and there is no point in waiting for the next 20 years to make good of that money. It doesn't happen. But that's what. So another thing what I want to emphasize is, as a small scale industry, because our products has been approved for reactor operation, we did shy away from the reliability criteria. We have met all the reliability criteria required, all the testing facilities required, and we have come out with flying colors. So I don't think in Indian industry really is worried about meeting the reliability standard of CERN or FAIR. I don't think so. If you require the reliability, we can meet it. I am very sure about it. So we do have the capability, engineering capability, design capability for that. But where we really get into problem is like that we invest, as Mr. Manis was telling earlier, we will invest a lot of money for making a 12-meter chamber or cryogenic chamber. When do we get back the money for that? When do we get the money back? Not after 20 years. That's the issue. So when DST or DE knows that somebody is putting an effort to do something as an indigenous project here for the benefit of the country, there should be some way to support them. It's not the paper saying that I'll give you an order. It doesn't matter. It doesn't make sense at all. See, we have made I can tell you something. We did make a product for a DAE. There's only a concept. They said we want this. So we took up the initiative. We made a product. We made a prototype, and we made a demonstration to the party concerned. And as usual, after they made a specification, it went for a tender. Unfortunately, we were not L1, and we didn't get it. So I'm not telling you we are not. I'm not sorry that we are not L1. We have put in a lot of effort to prove that. We have made an effort to make a patent out of that. We have made a demo for them. What happens to us now? How do we get a compensation? We cannot sell it to anybody else. That's what precisely happens to CERN or FAIR thing also. It's easy to say that you got a facility, you can try international tenders. It normally doesn't work. Basically because this product is made to order from a particular agency. Like CERN specifications are printed much earlier than it goes to tender. So for that tender only we have been making the product. So it's very difficult to find another buyer for that product. So my request to the fraternity here is, there has to be some address towards this. How do the people in the high places, help the Indian industry to meet this challenge? We can meet the technical challenge, I'm telling you. There's no dearth of technical challenge.
Your point is taken. Here I would like to make a point that in case of CERN or FAIR, I'm pretty sure that these tenders are basically the technical specifications are written very precisely, and there are stage-wise payments also, because there is a thing called series production and prototyping. So in case of prototyping, you get your monies back within 30 days of the delivery of the prototype after it is accepted. So those safeguards has been kept, and you have to build to the print.
But unfortunately, DST and DAE doesn't seem to go by that. No, I'm telling you.
I don't know. Maybe I missed the initial part of the question. Is the question is that whether the part payment is possible or not?
No, that's not. What I am trying to say is, when we take up a project, say national important project, as an indigenization project for DAE, I'm talking about DAE because I've been working with DAE, and we make a prototype as per your requirement, and give a demo to you. Normally we give a demo to you, and it meets specification. Then what happens? It meets the specification. Meets specification. That's what I'm trying to say. Then it goes for what you go? You go for a tendering process, right? There has to be 3 bits minimum. Somebody else will quote.
No, but just wait. I have exercised something which I am telling you for fair. I will not just give me. I will not tell you which exact product, because that's a different one. This was said that you get the whole contract, the entire contract of 100 items. Okay. You will build it. That's what is given. But the operational part of the contract will be valid only if your prototype meets the specification. Yes. So that's how the legal term is made. And the prototype has double price than the rest 99. This is how I have at least done 2 times for fair. And at least nobody of our legal team or purchase team complained. So this is possible. Now, and you said another thing is that if industry makes one particular item for CERN or fair or ITER or whatever, and then of course that item will not be repeated. Because that's this is absolutely true, because that's only for one fair, because fair is also one, ITER is also one, and they need this, and that will be the one. But my way of understanding the whole thing is that while reaching there, you generate I don't say infrastructure, it's an ecosystem, which will make many more products. Yes, so that's the only value addition that you have. You cannot expect that I will have 100 of that kind of order.
I do agree with you, sir. I do agree with you. But unfortunately, I'm talking about small-scale industry. So small-scale industry finance is much as important as the technical capability.
Yeah, that point is already taken, but it has to be noted that when you estimate and quote for a tender, that time you have to be very precise and you have to understand the job in totality so that you don't make loss. So whenever it is a single item also, you have to ensure that you don't make so that's what whenever I talk to any industry, I tell that you should not make loss out of it. Maybe the profits can be limited, but you should not make loss out of it. That is the mantra you have to maintain. And now with that, I will just open to the audience. If any questions are there for this panelist, we can take. Okay. If it is none, then we'll just call it a day. Yeah.
No, we have been following your mantra. We did take care of our R&D cost in a way, and unfortunately we ended up L2, and we never got it. That's the truth.
That will happen. But we cannot just dwell on one particular thing. No. We have to move ahead of that.
No. What I'm trying to say is, you say FON as well as CERN addresses things in a different way than what I have seen from DAE. So I was wondering whether DAE can also take that steps. That's all. Thank you.
Okay, that's it. So we had a very nice session, and we had a very different perspective from all the panelists. And I think we have made a note of all these points, and maybe both industries and us, we can improve that in future. Thank you.
So with that, we come to the end of Scientist Stage version 2. So on behalf of the Apex Committee of Vigyan Samagam, and in my own capacity as the convener of the Scientist Stage, the 2-day inaugural event of Vigyan Samagam, it's my pleasant duty to thank all the distinguished guests on the inaugural session, all the speakers of all the project sessions, the industries, the panelists, the directors and coordinators of all projects for presenting their best of their projects, and all your cooperation obviously was crucial for successful organization of this second edition. Sincere thanks especially to the VITM colleagues, Dr. Madan Gopal, Dr. Sadhana, Ms. Jyotika, Ms. Asif, Mr. Bharatan, and all the audio-visual, the team, the photography team, the videography team. I think without their constant help, we couldn't have done this event in time and so nicely. And I started yesterday by invoking J.R.D. Tata. Let me also end with probably one of his quotes. He said, I quote, "Despite all the difficulties and all the frustrations, there is a joy in having done something as well as you could." Here it has a second part, which is not so important in that part, but he says, and better than others thought you could. Okay. So with that, so see you again at Center Stage version 3 at Calcutta, the city of joy. And I'm sure all my Calcutta friends are here on 4th November 2019, and hopefully on a slightly different format based on various suggestions that we received during this and also the last session. So with that, thank you and have a pleasant trip back home. Bye-bye.
And for conducting this session in a very excellent manner,